Hello, my name is Brent Dalzell. I'm a research scientist with the USDA ARS in St. Paul, Minnesota. And prior to that, I was a research associate in the Department of Soil, Water, and Climate in St. Paul, along with Dr. Jeff Strzok. This is some work that we've been working on for the past few years. And specifically, I'm going to talk today about evaluating the Minnesota Agricultural Water Quality Certification Program conservation practice impacts on water quality in the Cottonwood River Basin. This work was funded by the Minnesota Department of Agriculture, specifically the Clean Water Land and Legacy Amendment funding. And I want to take a moment to acknowledge my colleagues at MDA, Heather Johnson and Bill Fitzgerald, Peter Gillitzer, and Brad Redlin. They were really helpful in many aspects of this work. And I also want to acknowledge that this work builds off of previously funded research that was funded by the National Science Foundation, as well as work that was funded by the Minnesota Corn Research and Promotion Council. This is a picture of the Cottonwood River near its confluence with the Minnesota. This is in Flandreau State Park near New Ulm. And when you stand down here at the water's edge, it's almost easy to forget that most of the land use in the Cottonwood River Basin is comprised of corn and soybean row crop agriculture. And that has a really important impact on water quality of the Cottonwood and subsequently water quality downstream in the Minnesota River and also the Mississippi River Basin. This is important because the Minnesota Nutrient Reduction Strategy sets out ambitious goals for reducing phosphorus and nitrogen loads into the Mississippi River, and much of the projected reductions that we need to meet in order to achieve our goals come from changing practices on Minnesota's croplands.
In order to provide some mechanisms to help farmers work towards achieving these water quality goals, the Minnesota Department of Agriculture has implemented the Minnesota Agricultural Water Quality Certification Program, MAWQCP.
It encourages conservation practices throughout Minnesota by providing technical support for farmers to help them implement farm-specific conservation practices. In exchange for participating in the certification program, farmers receive regulatory certainty for a period of 10 years following their enrollment. So if environmental laws in Minnesota change in that time period, their farm is already deemed to be in compliance with environmental laws. The certification program has hundreds of farmers and hundreds of thousands of acres enrolled across the state. One thing that the certification program does not include is on-farm monitoring of environmental runoff. That would be cost prohibitive and labor intensive. But still, we want to know, how can we quantify water quality benefits of the Minnesota Ag Water Quality Certification Program? One way to quantify those benefits is through watershed scale modeling. In this study, we use the SWAT model, which stands for Soil and Water Assessment Tool, to simulate a variety of agricultural management practices under varying weather conditions across the watershed. The SWAT model is commonly applied to agricultural landscapes and is suitable for simulating environmental runoff both from overland flow and also subsurface tile drainage, which is important for simulating water quality in the Minnesota River Basin. The SWAT model is capable of simulating many different components of the hydrologic system, and that's useful for us because the model can then help us to make sense of data that we measure in the field at different points across the agricultural landscape. Input data requirements for the model include spatial data like soils information, topography information, as well as land management information. In a large watershed like the Cottonwood, it would be impossible to collect detailed farm-level management information for all the farms in the watershed. So a typical approach in watershed scale modeling is making assumptions about typical practices that are common in the watershed. This information comes from farmer surveys, weekly crop reports, expert knowledge, and stakeholder interviews. Typical management data is combined with data from a variety of additional field-based sources in order to calibrate the model and ensure that the model is representing processes in the watershed accurately. Once the model is calibrated, we apply those model parameters to a nearby watershed in order to ensure that the model is behaving in a robust manner. Here, we calibrated the model on the Cottonwood River Basin, and we have validated the model on the Redwood River Basin. But again, the model was calibrated based on management information that's assumed to be uniform across the watershed. We know, because of programs like the MAW-QCP, that there are many farmers across the state who are applying conservation practices to their own farms, and so we wanted to set out to quantify the water quality benefits of the practices on these farms. Because of the certification program, we have farm-specific management practices for selected farms throughout the watershed. This allows us to characterize what conservation practices were in place on these farms prior to their enrollment in the certification program, as well as what practices they adopted as a result of their interactions with the certification program. This includes fertilizer application rates, tillage practices, presence of other practices like grass waterways, cover crops, wascobs, or water and sediment containment basins, and replacing open tile inlets with blind tile inlets. In order to incorporate this farm-specific management information into the model, we needed to make some changes to how the model was set up in order to track each individual enrolled farm separately. The model keeps track of information based on differences in land use, soils information, and topography. After breaking down that information into its constituent group, the model representation of the watershed might look something like this, with cropland shown in the brown colors here. But that does not reflect the changes that we need to keep track of for the certification program. In order to accomplish that, we added farm-specific identifiers to all certified farms that are located within the watershed boundaries. Including this identifier allowed us to keep track of very specific information on each certified farm in the watershed, and this was very valuable to us. In this example, I'm showing field-scale nitrate export from this particular farm over a 10-year period from 2004 to 2013. In this example, management is constant throughout this period, and so all of the changes in annual export are the result of differences in weather patterns over the study period. We can apply this approach to the entire watershed, as well as for the specific certification program farms. And by doing that, we can get farm-specific and time-specific information about field-scale export of nitrates, phosphorus, and sediment. A couple additional details about our approach. Management practice changes were only evaluated on cultivated land. There is some certification program land that's classified as either pasture or conservation cover, like CRP. We didn't simulate any changes there. And environmental outcomes from the certification program enrollment were simplified here to focus on 1 to 2 key management changes per farm. For this presentation, we are showing average annual values of sediment, phosphorus, or nitrate export for a 10-year period from 2004 through 2013. Each farm was given an arbitrary identifying number to keep track of information from one farm to the next, but no additional identifying information is given. We ran 3 sets of management scenarios for each certified farm in the watershed. In the baseline landscape, we assume management to mirror typical management across the entire watershed. That's shown here by the black diamonds. We also have farm-specific information before they were enrolled in the certification program. That's shown here by the orange triangles. And finally, we have farm-specific information for sediment or nutrient export after their enrollment in the certification program, and that's shown here by the green circles. Additionally, we list what conservation practices were on the farm prior to enrollment in the program. Those are listed on the right side, and you can see here in this example that this farm had conservation cover and a grass waterway. And the new practices in place are listed here next to the data points, and that is the installation of a blind tile inlet and fertilizer management practices. This figure shows average annual sediment export for all the certification program enrolled farms in the Cottonwood River Basin. While there are a lot of data here, there's a couple key messages to take away from this. One is that there is a lot of farm-to-farm variability in the degree of sediment export that occurs from these fields. That's typically the result of differences in soil characteristics and topography, and also in management practices. Two, the baseline landscape, the management practices that are assumed to be typical across the watershed, are the black diamonds and occur on the right side of this figure, while the certification program or the post-certification program data, the green circles, occur to the left. So, in comparison to a baseline landscape, most of these farmers are already implementing conservation practices on their farms that are achieving reductions in sediment export. In response to their enrollment in the certification program, nearly all farms achieved further reductions in their sediment export. This was most notably achieved through management practices like installation of blind tile inlets and also water and sediment containment basins. This figure shows average annual phosphorus export for the same farms in the Cottonwood River Basin. We see similar trends here, where there's a lot of farm-to-farm variability, but in general, the baseline landscape, the black diamonds, exist on the right. In some cases, the pre-certification condition is very similar to the baseline landscape, but in all cases, the post-certification condition, the green circles, occur far to the left and show the benefits of installation of practices, again, blind tile inlets and water and sediment containment basins, achieving most of the water quality benefits here. The story is slightly different for average annual nitrate export. It is worth noting that relative to a baseline management scenario, all the certification program farms exported less nitrate under the pre-certification and under the post-certification simulation scenarios. However, there are some scenarios, in particular installation of the WASCOBs, the water and sediment containment basins, that resulted in the models simulating less surface runoff but greater infiltration, which subsequently produced greater volumes of tile drainage. In those scenarios, nitrate export increased as a result of practices associated with enrollment in the certification program. It's also notable that the farms that have cover crops in place see dramatic decreases in nitrate export relative to the baseline scenario. Even following installation of WASCOBs, they're still showing some of the least amounts of nitrate export among the farms in this watershed. To summarize everything just one more time, the certification program farmers are already implementing conservation practices on their fields. In this figure, we can see that by the orange bars existing at relatively less rates of sediment, phosphorus, and nitrate export than the baseline condition, which is indicated by the gray bars. Certification program changes to farm management resulted in dramatically further reductions in both sediment and phosphorus export. But some of those same practices actually resulted in slight increases in nitrate export, most notably through increased tile drainage that came out of the WASCOB scenarios. Overall, this approach allowed us to compare management scenarios across certification program farms to quantify the water quality benefits that have occurred as a result of enrollment in this program. This approach and these results can help us to set realistic expectations for water quality benefits from program enrollment, and they can also help us to direct efforts for more farmer recruitment. If more detailed information does become available, we can include that in this approach, for example, expanding this along with some economic analysis to help decide where limited conservation dollars can be most effectively applied. Thank you for your kind attention.